This is a lesson in a series of lectures covering the use of bipolar junction transistors for basic single transistor amplifier topologies. And so far we've looked at some large signal circuit examples. And what we want to do in this lesson here is to look at some biasing techniques for biasing a bipolar junction transistor amplifier stage. So let me find that section. Okay. So we're going to look at a couple different biasing techniques, three mainly. And the first is the use of an emitter feedback resistor. So this resistor here will play the key role for helping us establish the operating current through the transistor. There's a couple different permutations, and we'll see that as we move through here. The second is to use a collector to base feedback resistor, and that is shown right here. This is a simpler topology, but is effective to bias up the transistor. It does have some fewer degrees of freedom, if you will, than the first one, but that's another one that's mentioned in the book, and I'll mention here. We'll work through it. And then thirdly, we'll be using a constant current source as depicted in this amplifier stage here. So we'll work through all three of those. So we found last time that if we were given a VB voltage, so if we were given VB and we knew the beta of the transistor, let's say that it's 100, and we were given the emitter resistance, then we could, and if we assumed a 0.7 volt or some voltage VBE drop for our base emitter junction. In other words, we weren't going to use the exponential Shockley equation. We were going to assume it to be approximately 0.7 volts. Then we could solve for the emitter current or the base current. And the emitter current would simply be equal to the total voltage in this loop, which would be VB minus the 0.7 volts, divided by the total resistance in the loop. But we would have to be careful to reflect all of the resistances to the side or to the branch whose current we were trying to find. So in this case, we're going to reflect all of the current to the, or all the resistances to the emitter side. Well, we have no resistor in the base, so all we have is the emitter here, and that would be the expression for the current. So if we had, for instance, 3 volts, and if we had 5K here, then we would have 3 minus 0.7 would be 2.3 volts over 5 kiloohms, which would be, what would that be, 460 microamps, I believe. Now, typically we're not going to have a voltage that's going to be provided for us like a VB. Instead, we will have a set of resistors RB1 and RB2, which will help set the bias voltage at the base, and through which will be supplied the base current for biasing up the amplifier or the transistor. Now ultimately we're going to couple the base through some capacitor to our input, and initially we'll look at an infinite capacitor, one that's just a short one, or open for DC and a short for all AC signals. So so the only thing that's going to affect the base voltage is going to be RB1 and RB2 along with VCC, and then whatever base current is being drawn through that into the base. So we need to simplify the circuit in order to make the analysis more straightforward. And so what we're going to do is we're going to take the VCC and RB1 and RB2 and we're going to Thevenize that. So we can redraw. Let me do it this way. So we have these two resistors, and we have a voltage source, VCC. And this is equal to a Thevenin source. That would be VCC times RB2 over RB1 plus RB2. And a resistance, a Thevenin resistance, that would be equal to the parallel combination of RB1 and RB2. So now we use this to redraw our circuit. We'll call this RBB, and we'll call this voltage here VBB. And the current now, IE, is simply going to be equal to VBB minus our VBE voltage of 0.7 divided by, now we'll have RE plus the base resistance but reflected to the emitter side. So as we saw in the last video lesson, we'll have the base resistor divided by beta plus 1. So that's how you would compute the bias if you were given a circuit with values. Now we can also consider a bipolar version of this same biasing or the same amplifier. And notice that in the one we just looked at, we were grounded. So we were at 0 volts and we were at VCC. Now we're going to have VCC and we have a negative voltage, that's minus VEE. So what we'll do is we can just tie the base to ground through a base resistor. Now you could have a resistor divider, RB1, RB2, that would connect between VCC and minus VEE, but that's typically not necessary. So I can write straight up by inspection now the emitter current. Again, we're going to go around this loop, and we're going to look at all of the voltage that is driving current to go in that clockwise direction, right, in a positive IE direction. And we will have VEE. So you might wonder, is it minus VE? Well, it's VE because let's say this is minus 10 volts. So the bottom of the emitter resistor is minus 10 volts lower than the emitter of the transistor. And so that would cause a current to flow downward or clockwise. So it's VEE. If you're not sure, just do KVL around the loop. VEE minus the base to emitter voltage drop divided by RE plus RB, and now we have to reflect RB to the emitter. And so you see this looks very much like the expression that we had here. It's almost identical. The difference is simply we have RB instead of RBB, and the driving voltage is VEE rather than VBB. Okay, let's move on. We're going to do some examples afterwards, but let's move on and look at the analysis for this collector to base resistor feedback bias arrangement. So in this circuit, what we have is, let's see, what do we have? We have the base current, the first thing to notice is that the current through the RC is actually not the collector current. So that's usually, we don't see that. Usually the RC has a current that is equal to the collector current. But notice that the current flowing through RC feeds both the base and the collector. In other words, the collector current, or the RC current, is equal to IB plus IC, which is IE. Okay, so the current going through RC is IE. Now, how much, let's look at let's think about the base current here. We've got the base current that is going to be equal to the voltage across RB. So that's going to be the collector voltage minus the base voltage. Now the base emitter voltage. The base emitter voltage is going to be 0.7, as we've assumed before, and that'll be divided by RB. Now VC is going to be equal to VCC minus whatever is dropped across RC. Now, if we want to solve for IE, we want to replace the base current with its emitter current equivalent. So the base current is equal to the emitter current divided by beta plus 1. I'm going to start rearranging this, so we'll multiply through by RB on both sides. We'll get VCC, and I'm going to collect VCC and 0.7 together, and then we have minus RC IE. Lastly, we want to collect IE terms together on the left, so we'll have RB over beta plus 1 plus RC. All of that is equal to the driving voltage, which is VCC minus 0.7. And now we can write that IE is equal to VCC minus 0.7 divided by RC plus the base resistor reflected to the emitter. And you might think, well, wait a minute, how is it reflected to the emitter? Is it not reflected to the collector? Well, it's the emitter because the current that is going through RC, again, is emitter current. So if we want to compare these two resistors, we have to get them expressed in terms of when they carry the same current. So this expression here, you'll notice, is again of the same form as the previous two. The driving voltage is now VCC and not VBB or VEE. And we have actually the collector resistor is acting as a feedback resistor instead of the emitter resistor. And then we have the base resistance again that's reflected through a 1 over beta plus 1. If you return to the circuit over here and we think just for a moment, can we picture how RC would actually produce negative feedback and kind of help to stabilize the current? Well, imagine that if the collector current, or the current through RC, the emitter current, which is the current through RC, increases, then VC voltage drops more. It would decrease because we get more voltage drop across RC. If it decreases, that reduces the voltage across RB, since RB has a voltage of VC minus the base voltage. When that happens, the base current reduces, and when the base current reduces, the emitter current reduces accordingly, and that then results in the voltage drop across RC reducing, thereby increasing VC. So you see that there's this negative feedback behavior. Okay, lastly, let's look at the bias for the case where we use a constant current source. This one is trivial compared to the others because we don't need to calculate the emitter current, because the emitter current is just equal to I. Right? Now we could say the base current is going to be equal to I over beta plus 1. And we can say that VB, the base voltage, is going to be equal to minus RB times I over beta plus 1. And we can say that VE is going to be equal to VB minus 0.7 volts. So this will be minus RB over beta plus 1 times I minus 0.7 volts. So that will situate our voltage VE, and then lastly VC is just going to be our VCC minus RC times, it'll be alpha times I. And that's really all there is to that constant current biasing arrangement. Okay, let's apply this now to a design example. So in this example 2.1 here, we have the classical emitter resistor feedback arrangement. This is what would be typically used on a discrete bipolar junction transistor amplifier. So if you go build a discrete unit in the lab, you might use something like this if it was a simple amplifier. The requirements for this amplifier is that IE, emitter current, is 2 milliamps. We want the collector voltage to be biased to 20 volts. And we want VE to be 10 volts. And finally, we want the current through the resistor RB1 to be less than or equal to 150 microamps. So if I didn't give that last specification, there would be quite a you'd have a lot of options in terms of RB and R2 selection that would actually be able to bias up the amplifier. So this rounds it out. Okay, so how do we approach this? Well, let's take the easy things first. We start off with 30 volts here, and we want 20 volts. Let's start even more easily. We start off with 0 volts here. We have 10 volts at VE. So we can write that RE is going to be equal to 10 volts VE over IE, which will be 10 volts over 2 milliamps. So that's 5 kilo ohms. We then can write that RC is going to be equal to VCC, if we call this VCC up here, minus VC, the collector voltage, over alpha times IE. Right, so this will be 30 volts minus 20, so that's 10 volts over, and our beta is 100, so this is 0.99, because that's beta over beta plus 1, 100 over 101 times 2 milliamps. So this will be 5, I'll just say approximately 5 kilo ohms. It's actually 5.05, but that's getting a little picky there. Okay, next, what we can do is we need to figure out the base voltage here, and we'll say we'll look at the base current. The base voltage is going to be easy. We just have the emitter voltage plus the 0.7 volt base emitter junction. So this will be equal to 10.7 volts. And the base current is going to be equal to the emitter current divided by beta plus 1. So that's 2 milliamps over 101, which is approximately 20 microamps. So let's now redraw this RB1 and RB2 network. We have 20 microamps flowing into the base. We have 150 microamps coming through RB1, and that means we must have 130 microamps flowing through RB2. Furthermore, we have 30 volts at the high end of RB1, and we have 10.7 volts at the low end. So we can write that RB1 must therefore equal 30 volts minus 10.7 volts divided by 150 microamps. And this evaluates to 128.666 kiloohms. Then we notice that the voltage across our RB2 is just a 10.7. So we have 10.7 volts minus 0 volts. And here we have 130 microamps. So 10.7 divided by 0.13 is 82.3. And we are now finished with our design. We can fill in the values here. We have 5.05 kiloohms for RC. We have 5.0 kiloohms for RE. We have 128.6 kiloohms for RB1 and 82.3 kiloohms for RB2. Now let's double check our answer here. So we're going to check. To check this, we want to do this Thevenin thing where we're going to replace our RB1 and RB2 with the VBB and RBB, where RBB is going to be equal to 82.3 in parallel with 128.6 kiloohms. And this equals 50.2 kiloohms. And VBB is going to be 30 volts times 82.3 kiloohms over 82.3 plus 128.6. And this ends up, let's see, 11.70 volts. So now we have 50.2 kiloohms, 5 kiloohms, and we have 11.7 volts. And IE then is equal to 11.7 minus the 0.7 volt VBE divided by 5 kiloohms plus 50.2 kiloohms divided by 101. And that ends up being precisely 2 milliamps. Okay, now let's look at a second example. Here we have again, it's an emitter feedback resistor biasing arrangement, but we have a PNP transistor, and we also have a bipolar arrangement. So we have a positive supply of plus 20, negative supply of minus 20 volts, and we're asked to bias up this amplifier stage to 1/2 milliamp emitter current. The transistor has a beta of 200, so we got to remember that instead of 100. We're told to have the emitter voltage to be 5 volts and the collector voltage to be at minus 10 volts. So let's begin with the easy stuff again. We can find RE quite easily because it is equal to its voltage drop divided by its current. So that's 20 volts minus 5 volts divided by 1/2 milliamp. So that will be 15 over 0.5 or 30 kiloohms. RC will have a voltage drop of minus 10 volts minus 20 volts divided by alpha times IE, which is going to be approximately, I will ignore the alpha because that's going to be 0.99, I think 5 in this case. Yep, 0.995. So this will be 0.5 milliamps. So we have a 20K resistor. Now let's calculate what voltage we have for VB. Now the base will be equal to the emitter voltage minus a VEB drop. Remember, for the PNP transistor, the diode is pointing from emitter to base, so we drop 0.7 volts. So this will be 10 volts, I'm sorry, 5 volts minus 0.7 volts, so 4.3 volts. And the base current, IB, will be equal to the emitter current divided by beta plus 1. So that's 500 microamps divided by 201. That is 2.488 microamps. So now we can calculate RB. RB is therefore VB over IB. And it will be 4.3 volts divided by 2.488 microamps. It's going to be very small, 1.73 mega ohms. Now we can check this answer by solving for IE as a function of the total loop voltage and our total resistance in the loop, and that is our VCC minus our VEB voltage drop divided by RE plus RB reflected to the emitter. So that will be 19.3 volts over 30K plus RE is the 1.7 meg. So we're going to divide that by 201. We get 8.6. We add that to 30, and then we take that and divide the 19.3, and we get 0.4999 milliamps. So that checks out.